Okay, so a brief summary of the lambda rule. So keep in mind these symbols that you see here, and in particular also keep into account that we indicated with the W the distance between the low water shoreline and the high water shoreline, with S is the beach advancement, okay, because the pre-project coastline is located in a position that is a distance S landward with respect to the new low water shoreline, okay? And the difference between low water shoreline and the high water shoreline is generally dictated by the tide. Remember that this distance depends on the tide excursion and also the slope of the beach. Because of course, if the beach is very sloped, it requires only a short distance to compensate from the difference in elevation between the low water shoreline and the high water shoreline. So W depends on the difference HWS minus LWS and the slope of the beach. I think this is everything we needed to summarize with respect to what we did last time. Do you have any question? Everything is clear? Okay, good. Now, let's move forward. This is a sketch, it's a typical situation that is good for getting the scheme, getting the concept, but of course, usually you don't have this such rectilinear geometry. In real cases, you may have a situation like this, and basically it's you see here also depicted the wave crest. The lambda rule is applied in the same way. So you see that lambda G is applied starting from the end of the T of the groin. So I start from here and I start from here, more or less. The distance lambda G dictates the position of the new low water shoreline. It may happen that the beach, in some cases, may advance more. So you can also see some more pronounced advance of the beach here. Usually it happens when the groins are much elongated. So if lambda G goes is reduced, because you may have also a smaller value of lambda, then you may get a different geometry. I mean, the geometry of the beach may follow this circular pattern, or more pronounced extension. It may come up to here and then close here. It depends on the real situation. Keep in mind that the lambda rule is a rule of thumb. If you want to estimate what is the real, or if you want to get a model that is more reliable, more close to reality, you have to apply a hydromorphodynamic model, which is typically a numerical model. The hydromorphodynamic model describes hydrodynamics and morphodynamics of the beach. So depending on the sediment transport, it models how the sediments get displaced. So keep in mind that the lambda rule is just a rule of thumb. So what is the purpose of the lambda rule? What is the usefulness of it? It is very useful when you have to make a preliminary design. But then, if you have enough information, enough resources, it may be a appropriate to apply a hydromorphodynamic model. Okay, we don't go into the details. There are some commercial softwares that are available. The only thing that I want to point out is that these models, these numerical models that are more complex, they have a higher complexity, usually require also more information. Information on the current morphology of the beach, on the sediment transport, on wave regime. Because you see here, for instance, we make reference to only one wave direction. Actually, usually in a beach, we have several wave directions. And for instance, the wave direction of extremes usually is not the same as the wave direction of ordinary storms. And it also depends on the season. So there are several, let's say, considerations that have to be made, which you cannot make with only the lambda rule, because the lambda rule, if you apply the lambda rule for several wave crests, several wave directions, then you obtain different results, and it's not clear how to combine them. The combination should be the different situations should be combined with a dynamic model. Dynamic means describing the system, the progress of the system over time, evolution in time. And therefore, the dynamic model takes into account that driver that takes place during the winter season has different features. And also with the dynamic model, you may take into account different beach managements that are applied during the different seasons. But still, as a rule of thumb, this is very useful. Another thing that I wanted to say here, usually we suggest that when we use the T-shaped groins, like in this case, we suggest, first of all, to align the direction of the groin so that the gap, meaning the segment that is connecting the two ends of the groin, is more or less aligned with the dominant direction of the wave crest. This is what we want to do. What is the reason? Of course, the sediments are coming more or less following the direction of waves. So we want to orient the gap in a way that most of the sediments are trapped. And you obtain this result if the gap is more or less aligned with the wave crest, so that the waves are really fully entering. They find the gap aligned with their crest. So they get in very easily. This is one first thing. Another thing that is important, if we are free to decide the orientation of the T-harm in the downdrift direction, here downdrift is on my left, on the left of the figure, it's here. Updrift is on the right of the groin. So when we are allowed to align it with some flexibility, it's better not to align it with the coastline, like in this case. It's better to bend it offshore, like it is done here. You see, it's not aligned with the coastline, it's inclined offshore, in the offshore direction. Okay, so basing on this situation, on this understanding on how it works, and this is also useful, a useful feature of the lambda rule. It gives us an understanding of what happens. Based on our understanding, let's try to summarize the steps that we can follow if we want to make a preliminary design of a battery of groins, of a sequence of groins. So let me move forward. We can identify 10 steps. They are very, they are not quantitative. These are qualitative steps. These are suggestions. You don't need to learn by memory all of them 10. But at the exam, you may get a question like, how would you design, how would you make a preliminary design of a battery of groins? And you have to be able to explain what is the driving concept, so the lambda rule, and then you should mention some of the indications that I will give to you through these 10 steps, but not really in the same organized matter as you see in the same organized manner as you see on the slides. You know, it's not really necessary that you learn word by word. On the other hand, you will see that these steps basically are easy to be remembered in their concept because they say some things that are to some extent also obvious. So the first step is that you have to know the wave regime. And this is, of course, trivial. You have to know the wave statistics, wave angles, which means wave direction, and the longshore sediment transport potential. So you have to get an estimate of what could be the longshore sediment transport through the, for instance, the CERC formula. Okay, and you know, it may happen that you don't have much information. So sometimes to define the sediment transport potential, it's not easy. And therefore, how to solve this problem? The first indication that I give is to try to look at the beach and understand from the shape of the beach, what are the main features? So where is located erosion? Where is located accretion of sediment, deposition of sediment? So is there already a structure like a pier of an harbor, of a small touristic harbor? Okay, if there is a pier, and what is the shape of the beach in correspondence of the pier? So you understand where is accretion and where is erosion. So accretion is located on the part is located on the part that is oriented updrift, the dominant updrift direction. Erosion is located downdrift. And there is a way to estimate what is the amount of accretion that you generally experience during a season. Like, for instance, we can get interviews and say, okay, now the shape of the beach is like this, so how it was last year? How was it last year? So last year the beach was different during the winter. How was it during the winter? So you can understand in the time window of a summer season, what kind of the amount of deposition, the amount of sediments, the volume of sediments that were given to the beach. Okay, the volume of accretion. And this is possible because usually erosion takes place during the winter. And then during summer, you have usually a dominant accretion because erosion takes place during storms. And then in calm conditions, you have accretion. And so you can get an estimate if you compare the winter situation to the summer situation. Of course, it's not much significant if it's for 1 year only, but it gives an indication like an order of magnitude for the volume of sediments. And so first suggestion is look around, try to understand what's going on. And this is something that you can do quite easily if you rely on your study, on what you learned here. And if you rely maybe on some additional information that you can get from the web, from additional educational sources, it's not so difficult. And the other suggestion that I give is look for similar places where the same intervention has already been done. So, for instance, you may be called to design a battery of groins in a location, and you realize that 3 kilometers downdrift, there is already a battery of groins that was built like 10 years ago. So if it is located just a little bit downdrift, it's likely that the conditions are similar. So you may go there, try to understand if indeed the conditions are similar, because on the beaches sometimes there are some singularities. But if the conditions are more or less similar, you may understand what happened during the lifetime of this battery of groins. And you may see how they were designed. And if they were designed in this way, probably there is a reason. And if the reason was wrong, you can see that it was wrong because you can see at the results. If the beach was successfully protected, then you can get inspiration from what others did in the past. You know, when you talk about sediment transport, when you talk about morphology of sediment, of beaches, the experimental verification is the most meaningful thing that you can do. Okay, so the direct experiment. This is why I also suggest, when it's possible, when designing these interventions, to keep flexibility so that you can adapt them later on. Take this flexibility, because the experiment, the direct experiment, is the most advisable situation, because these are phenomena that you understand, describing the hydromorphodynamics. There is a lot of uncertainty. You clearly understand that. It's already difficult to describe the waves. Think about the sediments. The sediments are transported by the waves, so they depend on your description of waves, but they also depend on additional processes that are not easy to be described, and therefore try to take inspiration from direct experiments. This is the suggestion that I give. Also because finding data, usually it's not easy. In the sea environment, in the marine environment, it's not easy to find data. And data of sediment transport, it's almost impossible. It's already difficult in rivers, so it's unlikely that you get data on sediment transport over the sea. It may happen if you're lucky, but it's not so easy. And another thing, if you have time, because you know these projects usually take a lot of time. So for instance, when we talk about dams, to build a dam, a medium-sized dam, we say that in Italy it takes 30 years. Since the inception of the idea, since the approval, since people say, okay, let's do it, we say it takes 30 years. If you are very lucky, it may take 10 years, but not less. So in the case of a beach recovery strategy, it takes longer because the dam is something, you know, you understand, huge environmental impact. You cannot step back. Once you built it, you cannot step back. With a battery of groins, you can step back. If you realize that the intervention was wrong, you can remove them. It's not a big problem. So it doesn't take so long, but it is not unusual getting all the permission that it may take like 3-4 years since when you decide. And therefore, it means that in principle, you have time to get the data. So you have time to set up a gauge of rain waves, or you have time to build some, I mean, a preliminary groin, an isolated structure, just one, and see what happens during a couple of years. And this is a verification of your intuition. If this is possible, this is my recommendation. Now, step 2, identification of the extension of the intervention. How long should it be? So typically, these erosions are local erosions. So there is a portion of the beach that is under erosion, and then after a change in the morphology of the sea bottom or the beach, finally erosion stops, and then you get to a place where there are no big problems. So if you can identify like the extension of the critical zone, then of course the answer is easy. Try to extend your intervention up to the full extension of the critical zone. Another consideration to make, usually these interventions are made in order to protect beaches that have a value. The value may be tourism, or the value may be an harbor. So basically, it may happen. You have an harbor over a beach, you want to protect the harbor. So another criteria may be that you just extend your intervention to the extension of the area that has the value. This means that downdrift, your intervention, you accept in a way, an increased erosion, because if you trap sediments updrift, then you caused an increased erosion or erosion potential downdrift. And you may accept this because maybe that downdrift you are not very much interested. You can afford a retreat of the beach downdrift. So this is an evaluation that you have to make by considering also the economic constraints, because of course groins take money. Okay. Okay, so this is step 2. Step 3. Where do you want to locate the post-project berm? Like, I need 10 meters more of beach. So you fix, you start applying the lambda rule, and let me go just back a couple of slides. You fix the position of LWS. Okay, of course, by taking into account that the more you advance, the more is taken in terms of resources and for building the groins, and the more the impact, etc. Now, so locate this post-project berm. Now, step 4, this is interesting. You should try to get a guess of the post-project slope of the beach. Keep in mind that when you stimulate accretion, you get a milder slope of the resulting beach with respect to the situation with prevailing erosion. And this is quite obvious to be understood. If you think of a calmer situation, you locate groins, you locate breakwaters, it's a calmer situation in terms of storm regime, of wave regime. So, and this is our purpose. We want to get a calmer situation because erosion is caused by more turbulence, by a situation that is not so calm. So in a calmer situation, of course, you expect that the beach is more gentle sloping. Okay, while when you have a strong erosion, you get a beach that becomes very steep. So you have to get a guess. How to get this guess? Again, this is something that analytically it's difficult to solve. You can apply a numerical model, but my first suggestion would be look around. Look around in a situation that is undisturbed and look at the slope of the beach in that situation. Or look into a similar situation. Sometimes when I say look around, the implication is that you don't look at a great distance from you. But actually, you may get a similar situation even in another continent. So provided that you have similar wave regimes, similar, I mean, it is possible to find inspiration from locations that are elsewhere, completely elsewhere, provided that you have good reasons for ensuring similarity of the context. There is a long literature on finding similarities in the environment for what concerns water resources management, flood protection. So there are several contributions in the literature precisely dedicated to this for water resources management, flood protection, identifying similar situations. And there are similarity measures based on some characteristic behaviors of the interested systems. For the marine environment, I don't have any information on contribution of this kind that have been made. But for sure, it is possible that you get information on similar situations, like the beach of the Adriatic Sea probably has some similarities with the beaches in Florida. Even if it's the ocean, maybe that you can get some indications there, okay? This is something, it's an example that just came to my mind, probably maybe not appropriate, but you have to look for a beach that looks similar. So you go over the Adriatic Sea, you look at the beach, and you think, okay, let's see on the web a sandy, mild sloped beach, where are located? And you may find situations that look similar. If they look similar, it is very likely that there is a real similarity, because you understand the look is the result of internal dynamics. And it is very likely that if they look similar, they are also dynamically similar. So you can get inspiration from interventions that have been made elsewhere. And this is one of the nice outcomes from globalization, you know. Okay, so step 5, prediction of the horizontal distance W between the mean low water and the mean high water shoreline. This depends, as I said before, W depends on the post-project slope of the beach. So once that you get an indication of the tide gap, of the tide excursion, you know the post-project beach, it's very simple. Okay, the distance W is very simple. If you make a sketch, a cross section, if this is the beach, okay, I exaggerate a little bit the slope. The slope of a beach, of a sandy beach, is much lower than this one. And if you have the low water shoreline here, low water shoreline, and the high water shoreline here, high water shoreline. So you have an estimate of the tidal excursion, okay, this one. This is the tidal excursion. So by knowing the tidal excursion and by knowing the, let's call it phi, post-project slope of the beach, then you can estimate W clearly with a simple trigonometric computation. This is quite obvious. Now, step 6, identification of the number of beach cells, number of groins. Let's call with the symbol lowercase n the number of cells. The number of groins is equal to the number of cells plus 1. Okay, the cells are the intergroin spaces. Now, you should also get a first estimate of capital G, the gap between the groins. And you should also decide whether you want to make a T-shaped groin or a non-T-shaped groin, okay? If you make the groin T-shaped, you reduce the length of the groin. If you think at the lambda rule, but we will talk about this later, if you think of the lambda rule, if you make the groin T-shaped, you can make it shorter. Okay, and we will discuss this later. Okay, so the number of cells, once it is fixed, we can express the length of the intervention, the length along the coastline, with this very simple formula. Number of cells times gap plus capital H. Capital H, remember that, I go back. So G plus capital H, and you multiply it by the number of the cells, and you get the length of the intervention. Okay? An approximate length of the intervention. And now you have to decide the length of the groin and the head width H. Okay, and how do you design this? With the lambda rule. So you have fixed the low water shoreline, the new low water shoreline, and therefore you then decide, okay, if this is the current beach and you want to put the new low water shoreline here, then you may decide, okay, let me just fix the groin here and another here. So you can make an assumption. You can make a trial and error procedure, and then you apply the lambda rule. You know the G, and so you apply the lambda rule, and you see, for instance, that with the lambda rule, you get the new position of the shoreline here. No, it's not good. And then you elongate the groin more, or you make it T-shaped. Okay. And we will see more details in the next slide for this. Here you see the sketch and the details of the computation. Now, I look at the second bullet point. If one wants to bring the low water shoreline up to the groin head, of course, then you have to use a T-shape groin. Okay. Look at the lambda rule. Sorry. If you apply the lambda rule from here, you may get a new shape of the beach, like the red line, and then you can bring, if you extend the width of the D, this is capital H, you can get the new low water shoreline up to the head of the groin. Okay. And this is the advantage of a T-shaped groin. If it is not T-shaped, as you can see from here, you don't reach the head of the groin. Okay. Now, so the lambda rule implies that, let's start from here. Remember that lowercase z is the width of the stem of the groin. Okay. The lambda rule implies that h should be, h is the width of the T, should be equal to 2 lambda g plus z. Okay. You can write equivalently that h half is equal to lambda g plus z, which makes probably the figure more immediately understandable. Okay. Now, let's move forward then by giving for taken this relationship. So, and let's introduce now the condition that it's the mean high water shoreline that reaches the head, not the low water shoreline, but the high water shoreline. So let's introduce a safety coefficient. So if we want to be very safe, we may say, okay, let's bring to the head of the groin the high water shoreline. So it means that the low water shoreline will be more extended offshore, in the offshore direction. And therefore, you may write it as h is equal to 2 lambda g plus w plus z. Or let's say, in general, let's indicate with the capital X the kind of allowance that we want to get with respect to the high water shoreline. So it's a kind of safety measure. okay? So I go back. Here it was 2 lambda g plus z, the width of the T. If I make it 2 lambda g plus x, x is a kind of allowance, okay? Where usually we recommend that x is greater than 0, because an allowance lower than 0, it's not recommendable, of course. And we recommend that the allowance is lower than W, because it's not really useful that we go to the beyond positioning the high water shoreline at the end of the groin. It's not necessary, indeed. Okay, now we can write this relationship, which is analogous to that we wrote before for expressing the length along the coastline of the intervention, the battery of groins, depending on what? The number of cells that we fixed, the gap that we want to make, lambda, the allowance x, or safety, and the width of the stem of the groin. So this relationship brings together what are design variables, like number of cells, like, for instance, the gap, like the Z, the width of the stem, like the allowance, and external information, length of the intervention, which usually is dictated by our input data, and also lambda, which is usually fixed. So basically here we have a kind of constraint of these design variables. And now the design aims to find an acceptable, the best combination of these design variables according to these morphological constraints that are dictated by the lambda rule. Okay, and if we manipulate this expression, so you see that in the second step, we just remove the parentheses here, and then we are rearranging according to the third, fourth, and fifth step, the equation in order to get an explicit representation for the gap. An explicit representation for the gap depending on the length of the intervention along the coastline, the number of cells, the allowance x, which you may set to 0, the width of the stem of the groin C, and the value of lambda. And now we have to play with these design variables, and how to play with them is the purpose of the last 3 steps of the procedure, how to play with them. You may remember that I anticipated to you that a gap that is lower than 20 meters, to give you an example, is not good. It's not good because, you get the feeling like you are in a prison, you go on the beach and you see the series of channels and it doesn't look like a natural environment. So it's not advisable. In the same manner, it's not advisable that you displace the groins at a distance that is larger than, say, 100 meters, because otherwise, they become a kind of sequence of isolated interventions rather than a combined set of measures. So especially if you see that the situation in the critical zone is tightly interconnected, it's not the sum of some local singularities, then in this case, it's better that you don't space the groin beyond kind of 100 meters, okay? So let's see, these indications are actually the steps to be discussed. They are 4. So some considerations. If the gap reduces too much, then it's better to adopt a rectilinear groin rather than a T-shaped groin, because, as I said before, otherwise the beach becomes like a sequence of pools, and also the exchange of water between the groins becomes much reduced, and water quality may decrease. So circulation of water, it's important, circulation and connection with the open sea. So if you get a very low gap, it's better that the groin are kept rectilinear. Now, so what is the moral of the story? Also, you have to consider this recommendation of 20 meters and 100 meters. So the recommendation is that in practice, we select a number of beach cells, N, for an identified value of lambda and desired value of X in order to keep the gap within a reasonable range. So let's say I want the gap of about 40 meters, much larger than 20 and lower than 100. And let's find then the combination, the number of cells that is appropriate to keep the gap within this range, okay, like from 30 to 50 meters. One thing that I want to say, if you put the groins too close, you also run the risk of generating rip currents. Rip currents, we discussed them a little bit. They are extremely dangerous because they are currents that have the capacity of bringing swimmers offshore. Of course, this risk is particularly relevant when you get hydrodynamic of waves that is particularly energetic. If you are in a beach that is not very energetic, then the rip currents usually are not generated. Usually, the places where we are exposed to rip currents are known. So when you get your preliminary information, you know this. There are several beaches in the Mediterranean Sea that are exposed to rip currents, and we know them. In the Liguria region, there are some of them where, unfortunately, some people died for this very reason. In the Adriatic Sea, they are not really frequent. And another thing, with recreational beaches, it is advisable that the distance between groins is larger than if you adopt T-shaped groins, is larger than the width of the T. So if you have gaps between the groins that are smaller than the width of the T, again, you feel like in a prison, you know, or in a closed pool. Okay. Now, the step 8, I already mentioned it. You have to position the gap and the heads along a line that is S plus lambda G seaward of the target design berm location. So what is S? Let me go back here. You see S. So you have to put the head of the groin S plus lambda G offshore. This is step 8. This is trivial. Okay, so in this way you decide the location of the end of the groin in the offshore direction. And then step 9 is orientation of the gaps in order to make the line connecting the groin extremes aligned with the wave crest. Step 10, you make a verification of the impact of extreme waves. This is quite important. And just try to, when you design an intervention, usually you refer to average conditions, to dominant conditions. Dominant means the conditions that are responsible for the evolution of the beach. But you should also make a verification of what happens when extremes occur, in particular if the extremes are particularly energetic. You know from the wave regime if it is likely that you get extreme storms, extreme waves, and if this is likely, if the waves and wave regime is energetic, it's better to make the verification of what happens in these conditions. And now the last step is to decide the landward extension of the groin. So the landward head of the groin should be extended to reach the pre-project berm, and the groin usually is buried into the beach fill. Okay, so you have to make sure that the groin is not bypassed landward. So the groin has to be extended landward at a sufficient distance in order to avoid any chance of bypassing. And there is one further step. I said 10, I forgot that they are 12 actually. So the elevation of the groin, elevation of the heads. So you have to minimize wave overtopping in general. So you have to minimize the likelihood that the groin is overtopped. So especially at the heads, and especially at the landward head, because overtopping at the landward head may lead to bypassing. And so the crest elevation basically should be higher than the design beach profile. So in a way, you have to keep the groin higher of the design beach profile in order to avoid that the sediment, the new sediment after accretion is blown out of the groin cell by extreme storms. And if you have a rock structure, usually it is recommended that the crest elevation should be not less than over the crest elevation over the post-project elevation of the beach should be not less than 1/2 of the armor stone diameter. Okay, now to conclude our discussion, let's look at the typical dimensions of groins. So what is the typical dimension? First, let's see how a groin is formed up. It's in the same way as a breakwater. So usually we have a foundation, and the foundation, usually the thickness of the foundation is between 0.5 meters and 1 meter. And the scope of the foundation is to distribute the weight of the groin uniformly over the sandy beach. Okay. And usually at the end of the foundation, at the upper limit of the foundation, we put a geotextile in order to protect the foundation. The geotextile is a kind of reinforcing of the beach, which is produced artificially. And then we have inside the groin a core. The core, I already mentioned this to you, is made by material with low permeability. And in order to get low permeability, the material is made up by very small grains, usually. We don't use clay. Usually we use grains which have very low diameter. In this way, the pores have also limited dimension. But of course, this material can be eroded. And therefore, we protect the core with an armor stone. And the armor stone is the protection of the core, but of course it's more permeable. So the purpose of the core is to reduce the permeability and also to create an inner structure that is capable of taking a lot of forcing. It's much resistant. Now, typical dimensions. So the depth, the depth H of the basement of the groin head with respect to mean sea level, usually it's from 2.5 to 4 meters. These are, of course, orders of magnitude. They are not fixed dimensions, orders of magnitude. RC is the height of the groin top with respect to the mean sea level from 0.5 to 1.5 meters. Okay. The depth of the groin basement landward with respect to mean sea level is about from 1 to 2 meters. Usually, you see that this is a different measure with respect to the depth of the basement of the groin head, which is the groin head. It's not specified here offshore. Of course, offshore you have the sea is deeper, and therefore you need a larger depth, lowercase h, offshore with respect to the depth of the groin landward. Okay. Now, B is the width of the groin top from 3 to 6 meters. Actually, there is no fixed rule for this. Keep in mind that some of the groins are equipped with a sidewalk so that people can walk along them and can reach the end of the groin offshore in order to fish, in order to swim. And therefore, if you have a sidewalk, it's needed a width of the sidewalk that is at minimum 3 meters. Some of the groins are not equipped for walking over them, and therefore it can be also the capital B measure can be lower than 3 meters. You may find groins that are about 1 meter over the top, and because if they are made by builders, usually, but this indication that is given here, of course, it's an average indication. The slope of the sides from 1.11 to 1.2, 1/2, not more than 1/2, and the thickness of the foundation, I already mentioned it. Okay, these are typical orders of magnitude. This is a question that may be asked at the exam. So what are the typical dimensions of a groin? You don't need to list all of them, but you should be able to say something like the width of the groin at the top is about 3-6 meters, and the slope of the sides is another important parameter from 1.1 to 1/2, and thickness of the foundation. If you can remember some of these numbers, I suggest you to remember them. Okay, now we skip this part, which is dedicated to hydromorphodynamic models. We skip it. Okay, we don't need to discuss this. I already discussed them a little bit. And I explained to you that these models allow you to make a rigorous verification of the effect of the intervention. But we skip it. At the exam, we don't ask for them. What I would like you to instead study and learn is this very simple formula to express the fraction of sand, capital F, that is transported beyond a groin, over a groin, which depends. So it is the fraction of sand that is not intercepted by the groin. The scope of the groin is to intercept part of the sediment transport, part of the sand that is transported along shore. But usually the purpose of the groin is not to intercept all of it, because otherwise it becomes too impacting, it generates too much erosion, downdrift. So our purpose is to intercept, to block only a fraction of the sediment transport, a fraction of the sand. And we indicate this fraction with capital F. We can express it in a very simple way, depending on the permeability of the groin And the permeability of the groin depends on how the groin is made. And if you have a groin with windows, permeability may be simply estimated as the area of the windows with respect to the total area divided by the total area of the groin. And permeability and a coefficient of bypass, meaning a coefficient between 0 and 1, also permeability is between 0 and 1, but capital B, coefficient of bypass, varies in the range 0 and 1 and expresses the fraction of the sediment transport that is bypassed at the offshore head of the groin, bypassed through the toe of the groin. So you see that the fraction becomes 0 if the fraction capital F, so the fraction that is intercepted, becomes 1 if B equal 0 and permeability is, sorry, I am getting confused. The fraction is varying between 0 and 1, that's for sure. But it depends. If you get permeability 0 and bypass 0, you get fraction 0. So permeability 0, bypass 0. So the F doesn't indicate the fraction that is intercepted, indicates the fraction that is not intercepted. Okay, I made a mistake. Is it clear? So when F is 0, you have F is 0. The fraction that is not intercepted is 0. So let me just see, transported over a groin. Let me make, I need a break already. So if P equals 0 and B equals 0, perfect, you have F equals 0, which means that permeability is 0, okay, and B equals 0. Okay, so it means that everything is intercepted and the fraction that is transported is 0. So permeability 0, B 0, F is 0, which means that everything is intercepted. And of course, because if you get permeability 0, so everything is intercepted by permeability, bypass is 0, there is no bypass, F is 0. Then, of course, there is a relationship between permeability and bypass. You cannot put all of them, both of them no, you can put both of them at 1. So let's put permeability 1, which means that the groin is completely permeable. And let's put also B equal 1. So the result is F equal 1, which is what you expect. A groin that is fully permeable and fully bypassable, then F, fraction of sand that is transported over a groin, is 1. Good. And then with different combinations, you see, you are able to understand the fraction of sediment that is transported over. Please remember this formula. This may be asked. Okay. Is it clear? Now I think it's better if I make the break, but let me, before the break, 1 second. Do you have any question related to this, given that I was a bit confused? No, no questions, okay. So p-values suggested by the literature. So you don't have to remember this. Just keep in mind that p-values are suggested by the literature. And let's forget about this formula here, because it's not important. And also permeability. Permeability is assigned through empirical relationship. Let's forget about them. The only thing, remember that there are empirical relationships for expressing permeability and bypass, okay? And here there is a couple of slides on one only slide for expressing bypass, but you don't need to remember them. And at this stage, we can make 15 minutes of break. Any other question? Okay, good. Okay, let's move to the next one, which is stability of rock and concrete armor units. It's strictly related to the design of groins. The last two links will be not dealt with by us. Okay, so they will remain there for your reference, but it's not subject for the exam, and neither for the lectures. And also this lecture on stability of rock and concrete armor units, we make today only the first part. I'll tell you later where we stop. 1 second, I'm checking if I don't think there is a PowerPoint. Okay, perfect. Now, what is the subject of this lecture? So, groins are made very frequently by armor units, or let's say they can be natural boulders or artificial units like those that you can see here. Boulders are used where there is abundance of this material, and therefore in the proximity of cliffed coastlines where I mean there is, as I said, abundance of natural boulders. Natural boulders, if they are readily available, are cheaper than artificial elements. On the other hand, their shape is irregular, which is not always a good thing, because we are also interested in their stability. And the stability of the armor units is, of course, directly related to the shape of the units. If the shape is spherical, you understand that the stability is reduced. And in situations where we have concerns related to stability and or there is no natural boulders readily available, we may prefer to use artificial units. And the artificial units may have a shape that is conceived in order to maximize the stability of these units once they are put together. I think there is available here a link with to a catalog of artificial shapes that can be used. Give me 1 second to find it, because I'm not sure it's available in this lecture or the next one. Just 1 second. It is, I'm using it just for giving you an idea of the shapes that can be used. Let me just 1 second. Okay, this is the figure I was mentioning. And these are the typical shapes that are used. The tetrapods are those that are most commonly used, but there are also some more articulated shapes like dolos, toscane, or corlock, or tree bars. You see that the complexity of these forms is conceived in order to maximize the capability of the units to connect each other, to block each other. I think there is also a link somewhere here where here to some Wikipedia page, and this is the page I wanted to refer to. This is a Wikipedia page describing the tetrapods, and you can see here how they look. I mean, the look is not so bad because, of course, the feeling is that artificial material do not give a good aesthetic to the structure. They don't have indeed a good aesthetic in principle, but you have to think that if you mix them with the natural material, and also you have to think that with time, they tend to assume a color that is to some extent similar to the natural material, because the color is not only given by the composition of the material, it's also given by the forcing, by the waves, by the chemical characteristic of the seawater, and it's also given by the activity of the ecosystems, of the bacteria, of the living organisms. So you can see that indeed they get, well, I mean, after time, they get quite well included in the natural environment. And here there is another example. And of course, this is relatively young. It looks like it is something that looks very artificial. But on the other hand, I have to say that I have seen several of these, because I always take the opportunity to look at how these structures are done, and also to gain an opinion on how they are built. And these are not so bad, I would say. This is another example. So you see that I think this is, no, it's in Crete. I was saying this is probably in Italy, but it is in Crete. They are very much used also in our beaches. And this is for the tetrapods. And here there is another link. These links, I'm getting them from another lecture, but you don't need to look at them for studying for your exam. I'm just using them in order to give you an idea. These are what are called dolos, or dolos in plural. And this is the shape of these dolos. And you see that it's how they behave. They are more articulated with respect to tetrapods. And but still, I mean, you see their size is significant. Still, they get, once that they are included in the natural environment, I mean, the look is not so bad, I would say. Of course, natural boulders are probably better, but you have to consider that this is an artificial structure, and it looks like an artificial structure. So it doesn't make a big difference, I think, in terms of aesthetic, if they are made by boulders or rather artificial elements. And also keep into account that if you are concerned by the environmental impact, there are other things to consider, like, for instance, the use of natural material, which has an impact itself, because you have to get the material from other places, and so it has also an impact. This is a figure showing the shape of the dolos. Okay, so let's go back here, stability. Okay, and here you see also here there is a picture of tripods. There are several of them over the web. Okay, so how to measure stability of these units? So given that, as we see, we have guidelines for the shape of the sides of the groin. These units, by the way, can be used not only for groins, so they can be used to protect the piers, as you have seen in the figures. They can be used to build breakwaters. And of course, you have to get an estimate of their stability in order to make sure that they are not washed away by the waves. Of course, you may say, look, they are so big, so heavy that for sure they are stable, but this is actually not true. And if you have witnessed some huge storms, relevant storms over the sea, you may understand that the energy of extreme waves is really huge. So they wash away cars and trucks without any problems. So, I mean, indeed, also the verification of stability is a task for the engineer, because we have to make a check. First, I make a premise. I am introducing now a couple of approaches in order to estimate the stability of armor units. These approaches refer to natural shapes. And therefore, we understand that if we use artificial shapes, probably we are on the safe side of it. If we use these theoretical, let's call them theoretical or experimental approaches that are valid for natural boulders. On the other hand, of course, we don't have to oversize protections. And if we have the opportunity of exploiting a greater stabilities for these elements, we have to do it. We have to take advantage of this opportunity. And therefore, the theory which I am introducing and the experimental empirical relationship that I am introducing is something to be taken as an indication, as a rule of thumb for natural boulders. Keep into account that the producer of tetrapods, dolos, artificial forms in general, usually they give you an indication which is derived by lab experiments or real-world uses, previous real-world uses of these materials. And in many cases, they give an indication for you on the stability, on the appropriateness of a given solution. Keep in mind that it is often the case that these producers, these providers of engineering solutions complete a verification for you. And it is quite common also for several other types of tools that you may use or engineering solutions. Usually the companies, the brands that provide you with the material that is needed for applying the solution are also able to provide you with a calculation, with an engineering design of the solution. And this is an opportunity that we have to exploit, of course. On the other hand, keep into account that when you sign a design project, you are responsible for it, and you cannot waive this responsibility. So you cannot say, I was told by the producers that everything was fine. So you have the duty to check if the information that the producers give to you is an information that is valid from an engineering point of view. And therefore, I mean, if you get kind of a lab certificate proving that the information is reliable, that's fine. And this, you can waive your responsibility, but you have to check this, okay? So, for what concerns us, I am introducing a theory, and keep in mind that it may be, and it is advisable that you refer also to the producer when you decide to use a specific form. The theory I am introducing is basically referring to two approaches. The first one is more theoretic. The second one is empirical. And the second one is the Hudson formula, which probably you already know, because if you studied breakwaters with Professor Archetti, it's very likely that she introduced to you the Hudson formula. You are confirming? Perfect. Okay. So the Hudson formula is the second approach that I want to introduce, and therefore I knew that Professor Archetti did it, and so I think we can skip it for my part. So I will not ask you Hudson formula, but maybe Professor Archetti does. So keep into account that you have also to be prepared on both the parts. What I would like to introduce today, and this is my way to conclude our adventure together, our lectures, is the Shields method. I think I am very keen on introducing it because the Shields method is, I think, very instructive. It is very instructive. In fact, it is applied, frequently applied to several applications. Not only in marine engineering, but also in fluvial hydraulics. The Shields method is a method to check the stability of sediments once they are exposed to an hydrodynamic forcing. So you have water flowing over a bed of moving sediments, potentially moving. Of course, we don't want they move in this case. And the question is whether the hydrodynamic forcing is moving the sediments or not. And this is what the Shield methods refers to. And let's start from a theoretical scheme, from a theoretical basis. So what we are studying is what you see depicted here. Okay, so what you see on the screen, so there is a boulder. Of course, the scheme is simplified. There is a boulder, the red one, which here it's schematized with approximately cubic shape. However, it's not a limitation, the shape, as we will see. This boulder is lying over a bed, which we assume it's flat, but inclined. Of course, the boulders in a groin or in a breakwater are not lying over a smooth bed. So we will need later on to consider the fact that the boulders are locking each other. But to simplify the scheme at the start, let's focus on this ideal situation. So a red boulder that is lying over a smooth bed, which is inclined of an angle beta with respect to the horizontal direction. And let's suppose that the boulder is exposed to a hydrodynamic forcing, which is the green arrow. And let's suppose for now, and we will see later the opposite situation, that the hydrodynamic forcing is pushing the boulder upward. Okay, so it's the wave run up. And let's forget the flashback for now. Okay, we will consider it later. So the hydrodynamic forcing can be expressed as a function of what? Of the area of the boulder that is exposed to the flow area. And the area here is represented through a characteristic dimension d, lowercase d, that is squared. Okay. Squared because it's an area. The characteristic dimension is what could be the radius, for instance, if the shape is spherical. If it is a cube, d, the characteristic dimension is the side of the cube, you know. So we have this hydrodynamic forcing F, which depends on this square, okay? And then it depends on the friction. It's called tau C here, no, only tau. The friction, the hydrodynamic forcing induces a friction over the bed, over the smooth bed, okay? And the friction is generating a tangential tension. So the tension multiplied, the tension is a force per unit area. Multiplied by the square of a length, you get indeed a forcing, okay? The friction, so the tangential friction, depends on the velocity of the flow, of course, and also depends on the type of flow, and of fluid. So the friction depends on velocity squared, as you may remember, because I'm sure that you have already studied hydrodynamic forcing. So the tau depends on the square of velocity and depends on the viscosity of the fluid and the mass density. Okay, so let's indicate it as tangential now forcing or friction. And I will show you later how, with empirical formulation, we can estimate that. Okay. And then there is a coefficient here. What is this coefficient, which is called C2? Yeah, it is a shape coefficient because it takes into account that the characteristic dimension may be multiplied by some coefficients in order to get the area exposed to the forcing. So if the shape is a cubic shape, then C2 is 1, because the square of the side of the cube is already giving the area that is exposed to the fluid velocity, to the tau. But if, for instance, the shape is spherical and the characteristic size is the radius of the sphere, you remember that in order to compute the area exposed to the fluid flow, you have to multiply by pi plus something else, okay, divided by something else. But in any case, whatever is the shape, you have, and if the producer, if you use tetrapod, the producer is able for the tetrapods to give you a characteristic dimension and the coefficient C2. And this is the forcing that is destabilizing the boulder, okay, because it's pushing the boulder upward. Okay, now what are the stabilizing forces? Essentially, it's the self-weight of the boulder that through friction between the boulder and the bed, the inclined bed, stabilizes the boulder. So the boulder stays there because there is friction. There is what we call in Italian attrito, which means that it's a kind of resistance. If you eliminate the friction, the boulder, even if not exposed to F, goes down and slips down. But there is friction which is taking, and the friction is proportional to what? To the self-weight. So I am copying from the figure there. If we are in this situation, you have a self-weight that is, of course, directed along the vertical, and I called it W, correct? Yes, W. This is W. And what is the value of W? Very trivial. You get the characteristic dimension cubed, the cube of the characteristic dimension, because you need the volume of the boulder in order to get the self-weight. You multiply the volume of the boulder, and the volume is obtained by cubing the characteristic dimension and multiplying it by what? By C1. It's a shape coefficient that refers to the computational volume. So it's different from C2. It's different. So it's indicated with the symbol C1. And then you have to multiply by the specific weight of the boulder. But let's consider the immersed specific weight, because the boulder is hit by water. So in a way, it is water is taking some of the self-weight, as you know. If we indicate with the gamma S the self-weight of the dry boulder, then we have to subtract, in order to get the immersed specific weight, the specific weight of salt water, gamma. Okay, so gamma S minus gamma is the specific weight of the immersed boulder multiplied by the volume of the immersed boulder, and then we get W. Good. W has two components. One component is aligned with the slope, with the bed, and the other component is vertical. Okay, and what is stabilizing the boulder is the component that is oriented perpendicularly to the bed of the boulder, to the side of the groin or whatever, okay? While the other component, which is aligned with the side, this is a destabilizing forcing. In this case, we are lucky because F is directed upward. So F is partially compensated by the self-weight, the component of the self-weight that is parallel to the side, but it's oriented downward, of course. And therefore, now we can compute these two components depending on the angle beta. So let me just here. This is beta. And let's consider that if this is beta, this is beta. Okay. And this is, of course, 90 degrees minus beta. Therefore, the two components are W cos beta. Okay, and this is W sin beta. Okay, so that's the explanation of this figure. Now, let's define the critical situation. The critical situation is given by subtracting these two components, destabilizing components. Why subtracting? Because we assume that F is directed upward. So at the numerator here, we put the difference between C2 tau C d square and sorry, here there is a tau C and here there is only tau. So there is a subscript that in one case is reported and in the other case is not reported. Actually, now I realize it's not a mistake. Why? Because we consider here the critical tau. The critical tau means the tangential friction given by the hydrodynamic forcing that is generating a situation of limiting equilibrium, of close to disequilibrium, okay? So it is correct that we identify it with tau C, because this is a generic tau. But here is the tau that is such that a smaller, even smaller increase of tau moves the boulder, okay? Minus W sin beta, which is the component, the blue one here of the self-weight, and the blue one aligned with the side. And then we put at the denominator what? We put here the stabilizing force, which is W cos beta, multiplied by the tangent of the friction angle phi, which is generating, you know, if you consider this component here, okay? And let me redraw it here, beta, and this is my W cos beta. This is basically, it's not the stabilizing force in itself. This is the self-weight in the direction perpendicular to the side. But if I want to transform this in the resistance force that is aligned with the side, the resistance force, the stabilizing force, I have to multiply this one here, W cos beta, by the tan of the friction angle. I think you have studied these concepts in other courses, okay? And did you get everything, or there is something that is unclear here? Now, look at the fraction there. When you reach the equality between the numerator and the denominator, you are in a limiting situation where the destabilizing forcings are just compensated by the stabilizing force. Okay, so this is the critical condition. It is expressing the critical condition. So what is our purpose? Our purpose is here. Let's assume that we know C1 and C2. It's not a problem. And let's then assume that we know W, and we know beta, and we know phi. So our purpose is to compute tau C. Okay, we know the characteristic size of the boulder, our purpose is to compute tau c. So what is the critical condition? Or our purpose may be to refer to a specific value of tau and compute the angle beta that is inducing critical condition. Now let's focus on the first question. Let's estimate the tau c, okay? Yeah. Sorry, phi. It's not represented here because it's the friction angle of the material. And the friction angle is defined as, let's suppose that you have loose material, loose boulders, and you throw them over a plane and they get a form after you threw them there. And it's a form it's a pyramidal form, essentially. So the angle between the sides of the form and the horizontal plane is the friction angle. Okay, and I think we can also find it here because I assume that you know what it is, but let me see if there is a Wikipedia page. I think this is the most, it looks like the simpler definition. Angle of friction, friction angle is a shear strength parameter of soil. Its definition is derived from the Coulomb failure criterion. And basically, let's say it's a shear strength parameter of soils, and it is obtained, I think, it depends on the coefficient of friction, μ, between the work surface and the indentor surface, where sliding takes place. Okay, so you consider the surface where the boulder slides over, and you consider the type of boulder, and the friction angle quantifies the resistance that is made against the slipping of the boulder by the combination of these two features. Okay, it's not in the figure. Okay. Okay, good. Now, so now we can develop this. You see, this equation is expressing precisely what you see in the fraction there. C2 tau c d square minus W sin beta is equal to W cos beta tan phi. And therefore, if from that ratio you want to get an explicit representation for tau c, this is given here, where W is expressed as indicated in the figure. And therefore, you get that tau c is equal to a multiplication of factor. The first factor is the ratio between the two shapes coefficients. The second factor is gamma s minus gamma. Third factor is d. And then you have the trigonometric part, the trigonometric factor, which is a combination of the two angles phi or phi and beta. I'm not sure if the pronunciation in English is phi or phi. It's phi. Or who is the best English speaker among us? Google would be the solution. Anyway, we will try later. So this is the explicit representation for tau c. And let's assume now, just for the sake of simplicity, because this is not a limiting assumption, let's refer to the situation beta equal to 0, which means a flat side. It's not, I mean, representative of our situation, but it's just for the sake of simplicity, for simplifying the relationship. And let's put C equal to C1 divided by C2. C is a characteristic parameter of the boulder, okay? Again, if you use artificial units, it is given by the producer. And then the expression, the relationship that you get, it's quite simple, okay? It's tau c is given by C tangent phi gamma s minus gamma d, okay? And then you can write it in this way. Okay, I deselect it, otherwise we don't see it anymore, which is very simple. And on the other hand, it's very simple, but what is the value of the constant? Of course, the relationship is simple. It puts into evidence what are the relevant parameters. On the other hand, we have a constant here that depends on the friction angle, depends on the beta angle, which we assume the zero, but if it's not zero, of course, the constant changes its value, and depends on the shape parameter, combination of the two shape parameters, C1 and C2. So, in principle, we have this relationship that is very easy and which allows us to compute what is the critical tangential forcing to be compared with the tangential forcing that we have in our specific situation, which we will see later how it can be computed. It depends on the waves behavior. It also depends on the currents, if any. But before we pass to that, let me say something more about this constant. First of all, actually, you understand that this parameter is not constant because we made some assumptions here. And first of all, before I move forward, here there is a wording and a premise which I think is extremely interesting, and therefore I am discussing it with you. On the other hand, I will not ask anything at the exam about this, but let me discuss it with you because I think it is interesting, okay? And so, first of all, what is the limitation of this relationship? Now, I want to discuss with you the reasons why the constant is actually not constant, okay? Because we made assumptions that bring us to say, okay, this is constant. Actually, there are limitations. So the analysis is simplified in the computation of the dragging force. Because, you know, we assume that the dragging force, it depends on a characteristic size of the boulder. And actually, the boulders may be a mix of boulders. There might be, I mean, it is for sure simplified. And it is simplified in the assumption that the right-hand side of the equation is constant and therefore does not depend on flow conditions. Okay? And so how can we get a more refined analysis? It can be get through dimensional analysis and Buckingham theorem. I am quite sure that you already heard about the Buckingham theorem. The Buckingham theorem basically looks at the units of in a relationship between variables, looks at the units of the variables and determines the structure of the relationship of the variables by looking at their units. And it is very useful because it allows us to identify what are the variable a process depends on. So what is the statement? Again, you don't have to remember it, but I think it is interesting. Let me select it. So if there is a physically meaningful equation involving a number n of physical variables represented by k physical dimensions, it means dimensions means units, then the original equation can be rewritten in terms of a set of p dimensionless number how many? What is the value of P? P is equal to n minus k, which means number of physical variables minus the number of physical dimensions. So in our case, what are the physical variables? Tau c, gamma s minus gamma, rho, mass density of seawater, because you don't have to look only at the equation, you have to consider at the general representation of it. D, the shape of the boulder, V, velocity of the fluid, particle. So how many variables are we have? 5. So this is the first step of the application of the dimensional analysis. You have to identify what are the relevant variables in a relationship. Now, these variables can be expressed in terms of 3 dimensions: length, mass, and time. So if you have 5 variables which are expressed depending on 3 dimensions, Buckingham theorem says that we can express the same relationships in terms of 2-dimensionless numbers. This is quite intuitive. Think of 5 variables that have 3 units, 3 different types of units to describe them. It is quite understandable that you can express the variables in terms of dimensionless numbers, and therefore you remove the influence of the units. The units are 3, the variables are 5. They can expressed by means of 2-dimensionless numbers. So this is why in fluid dynamics you find the Froude number, the Reynolds number, and the Mach number again in fluid dynamics. This is the usefulness of dimensionless numbers. They combine dependent variables together and allow us to simplify the relations. So what is the consequence? The consequence is that here we want to identify dimensionless numbers in this relationship. In the expression of tau c, the first one is obvious. It's the left-hand side of this equation. It's dimensionless. If you try to analyze the units of this relationship, it's dimensionless. And this is called the Schiltz number. This is why this relationship is written in this way, because Schiltz wanted to write it in a dimensionless form. So this is a Schiltz number. But there must be another dimensionless number here to be included here, which means that then the right-hand side is not constant, but must depend on the second dimensionless number. And what is the second dimensionless number? We don't prove what is, but it can be easily proved that it is the Reynolds number of the sediment transport, which is given by this relationship here. So what are the symbols here? D is, we already know what is D. Ni is kinematic viscosity of water, seawater in this case. It's a physical property. So if you don't know what is kinematic viscosity, go to Google, Wikipedia, and you find it. Okay. And U star is called shear velocity. And it can be derived in this way: is tau divided by rho, mass density of seawater, to the power of 0.5. So this is what Schiltz understood. He understood that this relationship, which gives tau c, must be expressed depending on 2-dimensionless number. One is this one, and the other one is the Reynolds, the particle Reynolds number. Particle Reynolds number is written here, sorry. So Schiltz, once he understood this, he said, okay, let me go into the lab and make experiments in a flume. He went into a flume, and the flume was inclined, And he got this graph here. This is the original graph by Shields. And in the vertical axis, you have the in the horizontal axis, you have the Reynolds number. Now, this is the original graph. It's barely readable, but I had to include it here because it is free, it is open access. But in order to better understand the shape of this graph, it's better if we look at another figure on the web, which is for sure not open, because I couldn't find any clearer figure that is open, unless it became available recently. So let's look for Shields diagram. Shields diagram, and here are the images. So let's find one that is nice, easily understandable. So this is the original one, okay? And let me see. The easiest one is this, I think. Let me open it in another, what happens here? Okay. Here it is. Now, so Shields parameter and the Reynolds number boundary. It's called boundary, which means close to the bottom. Okay, it's our number of interest. Shields derived this shape, and depending, he made several different attempts. So his curve was not a unique one. But if you take the average, you get this curve. And what is interesting is that we look at the high values of the Reynolds number, which means high velocity, which means high velocity of the fluid, which means full turbulence. Okay, and we are interested in this situation because on the sides of a groin, you have full turbulence. After wave breaks, you have full turbulence. So what do we see here? This value, critical tau, 0.0047. And this is indeed a constant. But it is a constant only for large Reynolds numbers. If you get to a situation with less turbulence, the critical value of tau goes down, so you get more instability, because if you have points located above this curve, it means moving units. Below the curve, stable units. So this means more instability. And then there is a situation corresponding to laminar flow, where if you have laminar flow, you have more stability, an increasing stability. So this is laminar flow, quite relevant stability. And then we have a transitional flow. The transitional flow is a mix between laminar and turbulent, and corresponds to the lower stability. And then full turbulence with a stable condition. Stable means constant value of shear stress. So this is the number we are interested in. We have to check that this is the critical situation. We have to check that we don't reach this critical value. We need to stay lower than that. When Shields made his experiments, he actually found a slightly larger value. His suggested value was 0.056. This is a bit reduced because then researchers made other experiments, and they suggested to lower it a little bit down. Okay. So I hope you agree. It is interesting. It is interesting because it allows to get into a practical demonstration of the application of a theoretical approach to a problem characterized by large complexity. So many problems related to sediment transport, where we need to find empirical solutions, have been tackled with this kind of approach. So you use a theory to get an indication of what are the relevant variables, and then you go to the lab in order to quantify the empirical part that remains unexplained. This is what Shields did. So basically, he understood what are the relevant variables, but on the other hand, in order to get to a quantitative conclusions, he went to the lab. And then several researchers made several experiments. And of course, you have to take into account one thing. The lab is an ideal situation. He used the sediments with the same diameter, spherical sediments, and therefore he didn't, I mean, he got reference to an ideal situation. Okay, good. Now, let's go back to our problem. So, because in principle, the problem is solved. Let's look at this relationship. Now we know that here we can use 0.047 instead of the constant. So we have defined the constant. We also learned that if turbulence is fully developed, it's indeed a constant. So now we can use this formula for verifying the stability of our units. But there is a but. First of all, how can we compute our value of tau? So the value that corresponds to our waves. Because if we want to check what is the value of this ratio and compare it with 0.047, we have to get a value for tau. Okay, so tau is given by two components, tau of currents and tau of waves. Let's forget about these relationships. Just let's look at their meaning. So tau of currents is related to the square of the velocity of the current, which is fine. This is what I told you before. And also depends on the density of water, as I mentioned to you. And it depends also on friction factor. It is a factor, let's say a factor, an empirical factor. But the dominant variables are square of the velocity and square of and density of water. Waves, currents are simpler than waves because currents, you have a current velocity and that's it. Waves, it's a bit of a problem because waves before breaking is one thing, after breaking is another thing. So let's consider before breaking what happens in the presence of waves. It happens that waves are only up and down. And there is actually no friction induced by waves. But there is a but. There is a small friction, which is due to the orbital velocity of the fluid particles. You may remember from Professor Archetti, not from me, that waves are just an up and down. There is no movement of fluid in the direction of waves. But if you look at any single fluid particle, they describe a small orbit, which is described with orbital velocity. And let me just show you one thing. I'm sure that you don't need this, but let me remain here because otherwise we lose our, and let me show you an animation which explains what is orbital velocity. So it's teaching, university lectures, and coastal engineering, coastal and harbor, it's mechanics of sea waves. And here you get, there must be a figure. It's not here, sorry. Beach hydrodynamics, maybe here. Here it is. This is the orbital velocity of the fluid particles. And the orbital velocity, the orbits are larger in correspondence of the surface, and their extension becomes smaller and smaller. We are interested in the orbital velocity in the proximity of the sea bottom, but we can compute it. We can compute it with this relationship here. This one. Yeah, this one. And we don't need to learn it. But this is the orbital velocity before braking. It's the velocity due to waves before braking. After braking, there are some relationship that are suggested, empirical, which are not shown here. And these relationships are different from run-up and backflow. So you have to make a difference between the wave run-up and the wave backflow, upside and downside the groin. Okay, but these empirical relationships are not reported here. Now, we have to take into account the effect of slope, and there are two factors. No need that you learn by memory. You just need to learn that the constant given by Shields 0.047 is modified depending on the slope of the side of the structure, because the shield experiments have been made with respect to a flat bottom, to a flat flume. It was not really flat, but close to being flat. And then there is another factor which is introduced, not reported here, for taking into account the effect of hiding. Actually, the boulders, the units, are not isolated, are not in the situation that is presented here. They are one against the other, and there is an effect of hiding. The effect of hiding is quantified through a correction coefficient. And then there is an effect of the armor unit shape that we take into account by referring to the producer. And then there is the Hudson formula, which I'm not explaining to you. So I am done. Before I make a summary of what we did together and I give you some hints on the exam, do you have any question? Sorry? I'll tell you in a moment. I said that I make a summary. You asked me if this part is asked at the exam. Yeah, I'll tell you in a moment, okay? I just wanted to know before we make our wrap up if you have any other question. Okay, so I propose that we make our wrap up in this way. Let's go back to the main page. So 1 second. Okay. And let's make a summary of what we did together. So forget about the last two links, okay? This is the easiest part. And forget about the first link. So first link, last two links, forget about them, okay? Good. So let's open one by one the other links. Second link. 1 second. Okay. Here, have a look, because this may be the subject of question. And for instance, a question may be classification of coastline, and maybe something like what types of coastlines did we consider? And then you have to say something about this. Of course, keep always into account, we don't need that you repeat word by word, or we don't want that you repeat word by word what's written here. The important thing is the concept. So you can use also a different classification. The important thing is that you refer to a classification which is, for instance, cliff costs, flat cost. And then there is a second classification, which is genetic, between emergent and submergent costs. This is fine. It's what we need, okay? And keep in mind the definitions. So it can be asked, what is a cost line? How would you define the cost line? Okay, and it is not necessary that you use the precise words that you find here, because there is no unique definition for cost line, but you should be able to say what a cost line is. Okay, and now I don't think here there is anything that you need to study for the exam. Once again, when I say that something is not relevant for the exam, don't take it as not relevant for your education. I mean, to find a job, it's not important how you passed the exam. It's not important, okay? To find a job, it's important that in an interview, you prove to the persons that are interviewing you that you know what they are talking about. You know what you're talking about, okay? And it's not necessary that you remember the Shields formula. For the exam, it may be necessary, but not for an interview. So don't take me wrong. If I say forget about these links, it doesn't mean that they are not important, okay? And keep in mind that you also need, your main target is not to pass the exam. Your main target is to pass the exam and then find a good job, okay? So this part here for the exam is not important. Okay, but it doesn't mean that I didn't do it for losing time, for finding something to say. I reported this information because I think it is important for you to understand what we are talking about. So I don't think here for the exam. That's it. Okay. Good. Port planning and environmental impact. I don't think here there is much to know, and I think what you should know here is this classification of loads. Okay, because the question may be, what kind of loads do we consider for designing a port? And then I think a good way to answer is we have loads from the seaside, loads from the berth structure, and loads from the land side. And then you can make a even partial list. For example, loads from the seaside are horizontal loads may be ship impact. Vertical loads, bollard forces. And that's it. I mean, you make an example, you say, okay, I have a clear idea. I know what I'm talking about, loads. Loads from the seaside, loads from the berths, and loads from the land side. For instance, to give you an example, loads from the seaside is the horizontal impact of a ship, and in terms of vertical loads, bollard forces. It's a perfect answer. You don't need to list all of them, okay? And berth structure, idem, one example of horizontal and vertical. Land side, horizontal and vertical, one example, that's it, okay? Usually I don't ask combination of loads, but it could be a question like, how do you combine different loads? I take into account the fact that there is, when the load are accidental loads, they don't usually overlap each other. They don't occur at the same time, while if I consider current loads, it may happen that I take the sum of them. Design life, same thing. What is the design life? And you say, what is? And for instance, breakwaters, typical design life is 100 years. Berth structure, solid structure berth, open structure, and that's it. And then I think that's it, okay? And forcing estimation, this is a bit more technical. So I may ask you a question about windrows. What is a windrows? And then you have to explain what is. And using fewer words as possible. Okay, you have to be rigorous but short. Of course, you have to find a good compromise between short answer and rigorous answer. Okay, and Probability may happen. How would you define probability? This is a typical question. And you don't need to remember anything more, relationships or just the definition of probability. What is return period? This is frequently asked. What is the return period? Okay, and then you have to say this. There is a definition here. Wind classification. It's not. You don't need to remember it. And now I already mentioned to you several times. Please learn this. Okay, and explain it. Also, try to be able to explain it. Okay, and only this one. The other ones, this is wind forcing. The other ones, wave forcing, no need to learn them. You know, this is, it is very unlikely that I ask this one. Maybe that I ask this classification of mooring lines if you really are a good student. So if you are a convincing student, usually what I try to do is to decide whether or not you really deserve 30 or the laude, I may ask a more difficult question. So maybe, can you say something on the mooring lines, how we term them, what terms we use to identify them? Could be, okay? And wave forces, no way. Return period, okay. Definition, not much more. And also this terminology here, usually I don't ask them, but try to make an effort to keep them in a corner of your brain, okay? Because again, if you get interviewed on something, it's, I would say that that's it. Now, Harbour oscillations. One possible question, what are the standing waves? What is a standing wave? Another possible question, there is the Merriam's formula. Forget about this math development description of resonance, no problem. And Merriam's formula, just try to remember this one. And that's it, okay? And be able to describe what is Harbour oscillation, what is Harbour resonance. So this may be the question. What is Harbour resonance? So try to find the words to describe it very quickly. I mean, it's no problem. Climate change, forget it. It's not a question, not a matter for the exam. And I would also say that it's very likely that you get a question on these strategies for beach protection, which is a classification. And usually we don't ask them because it's trivial. I hope that there is no need to ask the question at the exam. Okay, so for this link, beach protection. Design of groins, yes, the lambda rule, typical question. Lambda rule for the design of groin. And other typical question, main, what is the order of magnitude of the size of a groin? A typical question. Another typical question is, what would you suggest as limiting values for the gap between groins? So 100 meters, 20 meters, this is the answer, okay? And then stability, I mean, try to learn this. And if you are very good, I may ask, can you derive this relationship here? Which means that you have to make this sketch and to make this development here. You see, it is a fairly easy development. And I wouldn't go further, that's it. And then you may say, actually, this is not really always a constant because the shield experiments prove that it's constant in full turbulence, but in condition of transitional flow or laminar flow, it is varying. And that's it. Okay, a few more indications. The exam is lasting between 20 minutes and half an hour, the two of us. So 15 minutes Archetti, 15 minutes Montanari, or vice versa, and or 20 minutes Archetti and 10 minutes Montanari, or vice versa. And it may be 10 minutes and 10 minutes. Usually the questions are 3, max 4 questions. And usually we try to make a question that is general, like maybe something like, how would you design drawings? And when you get a general question, it means that you are allowed also to take some time to speak. So it's no problem if you speak 3 minutes or 5 minutes, because when the question is general, of course, you need to get into the context. And if the question is very specific, like what is the specific weight of seawater? Don't take it too large. I mean, just go to the specific answer. Okay, this is my suggestion in any case. So depending on the question that you receive in an exam, in an interview, you have to orchestrate your answer in a way that matches the expectation of the person who is asking the question. So if the person asks a very general question, like what is a car? You cannot say a car has 4 wheels. You have to explain to put it into context, okay? And if the person asks, how many wheels has a car? You cannot start by saying what is a car. You have to say 4, okay? Plus 1 spare, okay? And maybe. And try to understand what is the expectation. This is a general suggestion, and which I understood when I was a student, that depending on the character of the teacher and the way the teacher asks a question, you should develop an expectation of the style of the answer. And if you can match this expectation, is a winning strategy, because the person says, wow, it's precisely what I wanted to know. And don't make the mistake, which I did when I was a student. If you don't know an answer to a question, don't answer to another question. And this is something that I did when I was a student, and also noticed that many students do, because they feel like you cannot stay silent in front of a question. And I think it is much better if you have a problem finding the answer. If you have no clue of what the answer is, it's much better to say sorry. Sorry, I didn't know this was something that I should study. And if you have, sometimes it is unlikely that you have no clue. Sometimes you have some doubts. So it's much better to try to work with the teacher, like, I mean, manage the relationship, rather than giving the feeling that you are not cheating, but finding a way to deviate the question, you know. And so it's no problem, really. I mean, you don't need to answer all the questions to pass an exam. And of course, you need to answer all the questions if you want 30 with Laude. And also to keep into account that the Laude, in principle, we are suggested to give no more than 5% of Laude. It is a fraction that sometimes I exceed. I have no problems, but keep into account this indication, which means that, you know, if you aim to the Laude, you should really prepare well on you have to really convince the teacher that you are passionate about the topic, that you made a real effort to get into it. And in general, the average mark of our exam between me and Professor Archetti is quite high, because I think it's also a merit of the students, and also you see the topic is not a difficult one. In your career, for sure, you have tougher exams than this. Questions? It's 2 p.m. Yeah, and were you here when I made the sketch? Okay, it's 2 p.m. And if there are some changes, we will let you know, but I don't think so. It's next week, correct? Is in next Thursday, yeah, Thursday, yeah, because today 8, no, 8 plus 9, oh no, Thursday, yeah, Thursday. So Thursday. Yes, no problem. Me or Professor Archetti. Try to address the question to the person who taught the topic, okay? And yeah, otherwise we have to bunch the questions between us. And I already mentioned at the start, I'm not sure if you were here, that if you want additional dates, you have to just send an email. Because it may happen that at the last minute you decide not to attend the exam. It's not a problem. Just send an email and let us know. And it may happen that you decline the mark. If you decline the mark is not recorded. You can repeat the exam at the next round. And the only thing that we ask is to allow us at least 2 weeks between one round and the next. But you can come after 2 weeks if you want to decline the mark. It's no problem at all. Okay. Thank you very much, because you made an effort to attend, and I really appreciated it, because it was important for me. When you are few students, it's really important that you make an effort to attend. When students attend, it's much more stimulating. I also want to apologize because in a couple of issues I made some confusion, Harbour oscillations especially, and I hope that you got it at the end of the story. Okay, good.